Yep. Yeah, I'll take 2. Yes, with extra. Absolutely. Okay. Right on. Peeps, what's up? Okay. We got a new topic. It's actually quite delightful. A little bit easier. It does rely on some previous skills, but what I like about it is that the units in the end are what are called scalars. They are not vectors. They don't matter where they point. So it's just a number we come up with in the end. So here we go. The topic is work, power, and energy. And the definition of work you might think is related to effort, like how much work you put into something, or I work out at the place that pays me and they will pay me because I work for them. Well, that's a definition of work, but in physics it has a very specific meaning, and it means this: when a force pushes or pulls on an object parallel to its displacement, that force performs work on that object. So mathematically, here's what it is. We've got work is defined as the force parallel to its displacement, so parallel to its motion or its velocity. You can think of it that way too. Force parallel, that is not an 11, that's actually the parallel symbol, times its displacement, or if there's an angle involved, which quite possibly there may be, then it's related to force times the cosine of the angle times d. And we've got a new unit. Now you might realize that, hey, a force is measured in the unit of newtons, and of course d is measured in meters. In angles we really don't represent as a physical unit, it's just kind of a measure of the arc and whatnot. But here we would have newton meters, and you might think, hey, we can call work a newton meter. And you could, but there is a problem with that. It's not established in the System International. That is, we have a unit that's actually named after somebody who's quite a famous scientist named James Joule. So the unit here for work is joule. And one of the funny things is that we'll actually deal with newton meters later on. Not for work, but another unit for a quantity known as torque, which is essentially, it's like force causing a rotation. And so newton meters will be reserved for something else, and it has a completely different meaning. So the context doesn't get mixed up by calling two things newton meters. We'll call this one a joule. And there we go. We'll work with 4 examples, quick examples coming up of how we can calculate the amount of work performed on an object. Example 1, frictionless, no friction. So here's our situation. We have a force applied acting on an object, a 5 kilogram crate of some sort. Could be kittens, I don't know. We saw them before, so why not? They may be inside. It's going to be displaced 8 meters, so it shall move 8 meters to the right. So I really should establish a coordinate system to indicate which direction is positive. So that's positive x and positive y, like that. And this object is on a frictionless surface. Just to make it simple over here, we want to calculate the amount of work performed on this object by this force. So by definition, we have work is equal to force parallel times d, or that's also force times the cosine of the angle times d. And the cosine of 0 is 1, so this is 0 degrees. There is no tilt to that force at all. So all we have here is a very simple calculation that says we have a force of 100 newtons times a displacement of 8 meters, and altogether we have work performed on this object of 800 joules, like so. Example 1 is done. Example 2, frictionless, but with an angle. Hey! Our situation is very similar to what it was before. We have our 5 kilogram crate of kittens. This time, it's pulled with the same force applied, but at an angle of 40 degrees with respect to the horizontal. The distant displacement of this crate will be the same, 8 meters. So again, we want to determine how much work was performed on this crate by this force. Okay, again, important to establish the coordinate system, positive x, positive y. Okay. What we have here is the definition of work. Once again, I'm going to go right to the one with the cosine since I've got an angle. So work is force times cosine of that angle. So what we have times the displacement, but of course, and what we have here is 100 newtons times the cosine of 40 degrees and times 8. Okay, so this part over here is about 76.6 times 8. Let's go figure it out. All right, I've got 7.66 times 8, or 76, 612. We'll call it 613. Let's round up. All right, so this time the amount of work performed is 613 joules. Okay, notice it was less than the work performed before. Part of the reason, of course, is that now we have this angle, and this value is less than it was before with the 100 newtons. Before it was 800 joules. This time it's 613 joules, so less work is performed. What that will mean is that this object will possess less energy. There's an equivalence between work and energy that we will see soon. What happens is that this work actually gives this crate kinetic energy, the energy of motion, and it will do so with a little bit less because of this angle over here. We know that not all of this force is going to be used to move this crate in the forward positive x direction. Some will actually try to lift it above the ground, so there's less available to speed this up. So if we were to calculate the acceleration over 8 meters, the acceleration would also be less than it was before due to this angle. All right, so here it is. Number 2 is through. Example 3, with friction. Mu kinetic is 0.4. What we have in this system is the same thing as before, except we've added friction. Force applied is 100 newtons at an angle of 40 degrees. We found that value before, and it would be good to park it. Once we develop things, we'll be able to use the results from example 2 to solve example 3. So this force is still going to do the same amount of work on this object. However, we have friction performing work in the opposite direction. So once we establish our coordinate system, the same one as before, positive x, positive y, in the positive x direction, in the direction of displacement, this force applied shall do positive work on this crate. Friction, because it's pointing in the opposite direction of this displacement, is actually going to do negative work. Work can have a negative value. What it basically says is that we're going to try to give this crate kinetic energy, the energy of motion, by applying this force. But this resisting force over here, the force of friction, will try to take some of that away. So the net work, the net amount that this crate shall be left with, will be less than it was before, which totally makes sense. It won't be moving as fast, and so it will possess less energy as well in the form of joules. Well, let's set this up. What we have from before is that work equals the force applied times the cosine of the angle times d. Now we're going to subtract that, because friction is in the other direction, times the force of friction times d. So we already have the negative involved here, all right? And we're going to just figure this all out as it is. Well, this is the value that we had from before. Angle is 40 degrees. Now friction will not have an angle, because the force of friction, the nubblies here, are always going to produce a force that is directly in the opposite direction of this motion. Okay, so we don't have to worry about angles with frictions. That's kind of nice about friction, believe it or not. We don't have to worry about that. We will have to worry about it though in terms of how do we calculate the amount of friction? Well, we've done this many times before, and we have to take into account the normal force and the effect of this force applied pulling upwards somewhat. Okay, so we know that the force of gravity, mg, will be pointing down here, and we've got the force normal, because this is on a surface. That's why we have nubblies, right? I mean, if we weren't on the surface, there would be no nubblies in contact, therefore no friction, but it is. Okay, so this part here will take a little bit of processing, right? Because we know that this is equal to mu times force normal. Okay, mu is 0.4. Well, what is force normal? It's not just mg. It is actually, if we sum of the forces in the y direction, we've got force normal in the positive direction. All right, so this is the net force, the number of pushes and pulls in the vertical direction. We have force normal pushing up, mg pushing down, and we have the vertical component of force applied. So we have minus force applied, it's in the up direction, plus force applied times the sine of 40 degrees equals 0. It would equal ma. It would, if there were acceleration, the a would exist. But the thing is, if we have a normal force, there can't be an acceleration in the upward direction. By definition, it's resting on the surface and does not have an acceleration upward or downwards. Okay, so let's try to find some values now. So now we have this great thing over here where the force normal equals mg minus force applied sine of 40 degrees. Right on. All right, so this thing is starting to develop a little bit, and it actually becomes, I think I'm going to do this in a green. I just feel green. Okay, so force of friction is equal to mu times force normal, which is this over here in terms of the values that we have. We were given mass, we know what g is, and we were given force applied in the angle. So we want to always work it out in terms of the variables that we know. So it's mu times mg minus force applied sine 40 degrees, and all that times d. All right, so that's that term over there. All right, and together, what we're going to have is the value in joules of the amount of work actually done on this. I'm going to calculate these separately as numbers at the moment because we have all the variables there. Work is F cosine theta times d, minus mu mg, mu times the parentheses of mu mg, the minus force applied, sine of, I should put theta, but in this case it's 40 degrees, times d. All right, so everything is here. We've got everything solved out, so that's cool. We might remember from before, number 2, this is 600 and I think it was 13 joules. Okay, let's find out what this is. All right, so we have 0.4 in parentheses. Now we got m, which is 5 times 9.8 minus force applied sine 40 degrees. Okay, so we have 100 sine 40, and all that is times 8. So the only one that I'm a little concerned about in terms of calculating is just this part over here. I can do the rest pretty much almost in my head, but all right, 5 times 9.8 minus 100 sine 40. I'm in degrees. That's 42.6-ish, okay? Times 8 times 0.4, I get about 136, all right? So altogether, the negative work performed by friction was 136 joules. So it's interesting to note that the positive work done by the force is still the same. Now there's negative work done of 136 joules by friction, and together they give us the work done on the object, the work performed on the object, which you can call net work, or just consider it the total work done on the object. And so what is that? 613 minus 136, so about 477. So we keep going down, 477. So work total on the crate is 477 joules, like that. 3, it's time to set you free. Example 4, the inclined plane. Inclined plane. Muse point 4, kinetic. Remember this guy? You like him? Here's the deal. This time we put our 5 kilogram crate on an incline. Since we used 40 degrees before, we'll use it this time as well. The incline is 40 degrees. And what we have here actually is a free body diagram. Technically, the free body diagram would not have the components. It would just have this thing called mg, but I like representing it as the components here, which is one that is parallel to the incline and the other one that is perpendicular to the incline. And so this time when we establish the coordinate system, it shall be rotated accordingly, so that positive x is on the parallel segment and positive y is the perpendicular segment, like this. So our situation now is that we want to try to find out the work performed by gravity against friction. Gravity is responsible now. There's no force applied, but gravity will want to slide this down the hill. So we want to figure out the work done by gravity and then the work done by friction and see what the total work performed on the object is, this crate. All right. So we'll go the same distance, 8 meters down this incline. And so we're going to start like this. The work is performed along the x-axis. So we'll just write that equation down. So we have work equals, in the positive direction, it's just mg sine of theta. That's the component of gravity that'll do positive work in the direction of displacement. So we got work is mg sine of theta, that's the force, times d, and we'll have minus force of friction, kinetic, times d. And just like before, the whole thing with friction is what gives us a little bit of finagling to do. So this guy over here, as we know from last time and from our study of friction and forces, is that this is mu times force normal. In some respects, this is almost easier than the last case, and I'll tell you why. Because force normal is going to be equal to this component of gravity, mg cosine theta. We don't have to analyze it in any other situation, like, oh, what forces are going up in this direction and down. It's just this one down, and it's equal to mg cosine theta. So this is just equal to mu mg cosine theta, just like that. All right, so it becomes a little bit shorter, and I'll write this whole thing down in symbols first. So we got mg sine of theta times d minus mu force normal, which is mg cosine theta times d. If I were really fancy, I could factor this out, factor a d out. I think I will be that fancy. Why not? Haha, we have this great ability to do that. D, I can factor out an mg as well. Ooh, this is really getting kind of exciting. D times mg. Whew. All right, dmg. I know that. That's like a Mac thing. Times sine theta minus mu cosine theta. Now, this whole thing here is the work done on the system. What might be interesting is that we could also find out the amount done by gravity down the hill, and this is the amount performed by friction. But let's just calculate. I'll let you do that on your own to see if it works out. This is going to be the total amount of work. And if it's positive, as it should be, then that's the stuff that's left over. That'll be the amount of work performed on the crate, and it's also going to allow us to determine how much energy it's been given in terms of what's known as kinetic energy that we'll study next. All right, well, let's plug into some numbers. So we got D, the same 8 meters that we had before. M is 5 kilograms. G, 9.8 meters per second squared. And the thing here, I will need a calculator for. All right, so we got sine of theta. So sine 40 degrees minus 0.4 times cosine of 40 degrees. And in there, it's 0.336. Let's go with that. 0.336. And this is it. All right, so we have 8 times 5 times 9.8 times 0.336. And 131 is positive. Yeah, all right. So, as we knew, 131 joules. All right, approximately 132 if you want to round it, but this is good. So the amount of energy, the amount of work performed on this crate in total is 131 joules. That also means that it now possesses 131 joules of kinetic energy. So we'll get into that in a little bit. And so that's what it is. Number 4, you're out the door. See ya. Morad, out.